Hi everybody, this is Sushant again, and I'm trying to put together a quick lecture on the transmit chain. Thank you, first of all, thank you all for watching all the videos on YouTube. I hope you're learning from those videos. I've had some good comments and some requests, and this is one of them. So I'll try to put something on the transmit chain. This lecture is not focused on going through a great bit of detail about everything that is there in the transmit chain, but this is mainly focused on the linearity, which is a key spec in a transmitter, and specifically what you must have heard of, like in terms of ACPR. It's called ACPR, or also called as ACLR, which all come out from linearity, and how or what are the things that we just fundamentally need to understand, that what's going on, and also go through some of the circuit details of it. So that is what this lecture will focus on. This lecture will not go into the details of like how you design each and every block, what is there. Many of the blocks are like, there are some filters, mixers and all. So I won't be going into those blocks and going into a lot of details through those blocks. Now I will mainly be focusing on ACPR, how to derive ACPR, how to do some simple hand calculations so that we can do an initial hand design for ACPR of some of the critical blocks, which I will kind of go through here. And I'm trying to do this to hopefully keep this lecture short, because one of the comments I heard is some of my lectures are too long, and so I'll try to see if I can squeeze this in 30 minutes so that you don't have to watch it like break it up and watch it in many sessions. So let's start here by first talking about OFDM signals. Most of the things that we use now, in the cellular world, whether you have WCDMA, CDMA, LTE and all, we use certain things called OFDM signals. I have mentioned it earlier. You can look it up in Google, what does OFDM signal means and all the theory behind it. But the bottom line is, when you have a transmitter and the transmitter is transmitting out something in a particular band, in a particular channel, I should say a channel, which is what I'm trying to show here as this dashed outline here. It is not actually transmitting a single carrier. It is actually transmitting a bunch of subcarriers. We call it subcarriers. For example, here I'm only showing two carriers here, which is there in this mask, but in reality it's not just that. There are thousands of subcarriers based on how wide is your bandwidth. For example, if you have an LTE system, LTE 5 megahertz, 10 megahertz, 20 megahertz, you could have thousands and thousands of these subcarriers, where each of these subcarrier carries particular information, and that's how you transmit it. If it's Wi-Fi type system, there also it's the same thing. You have a lot of subcarriers that are being transmitted in a particular channel. So if this is your channel, then you are actually able to you transmit a lot of subcarriers that goes through it. So that is what we call as the OFDM signals. Okay, so here, rather than showing a lot of subcarriers, what I've done is I have tried to squeeze it and show just by using two subcarriers to explain the concept of what happens when you have two subcarriers and you actually pass it through nonlinear systems. For example, well, I have a TX chain picture somewhere here, so I'll try to see. So this is, let's say we have a TX chain like this, right? And sorry for the distraction, I'll go back to that picture again. But a chain could have DAC. This is where the digital bits are coming from the modem, that passes through some filter. Then you have a mixer, which is going to upconvert that information into your 900 megahertz, 1800 megahertz, 1900 megahertz, 2100 megahertz, whatever your band is. Then you have some sort of a DA. DA is driver amplifier, or also called pre-PA, pre-power amplifier. Then it goes out of the chip, and PAs are normally a different chip. Mostly they are gallium arsenide. That's why I've shown it as a single in it here, but it goes to a power amplifier, then a duplexer, and goes out. Each of these elements will be nonlinear. If you put signals to it, they're going to have their second order distortion, they're going to have third order distortion, fourth order, fifth order, and so on. Typically, if you process in differential mode, then you don't have so much of second order distortion. That is your assumption, which is true most of the time. But even in sometimes, the second order distortion could also come up if the swings are too large and the system start to get saturated. So, but still, let's assume the second order distortion is not much. You have third order distortion, or in a way saying you don't have so much of even order harmonics, but odd order distortions are there, more like third and fifth. What can they actually cause at each of these stages? They are going to create some nonlinear components which is what is going to be the unwanted signal. They will start causing noise, and eventually they end up becoming the reasons why we have something called ACPR and ACLR. That's how they are generated. So let's come back to this picture and we say, okay, if we have two tones like this, okay, as I mentioned, there are lots and lots of subcarriers, but I'm only considering two tones. Then we know that if you only consider the third order intermodulation, okay, we will have a third order component here, which I've shown as IM3. Okay, this delta between all these tones is equal. That's hopefully you know from the concepts basics of RF, the fundamentals there. So this IM3 that is generated here, you can see is it first falls in band. This is what we call as in band IM3. Now our signals are these subcarriers. These red ones were never there and we don't want it. So this is unwanted garbage which is going to act as a noise. So in scenarios like this, if two tones were kind of like this here, where its IM3 falls in band, it actually acts as a noise and it affects the SNR. So imagine such a thing coming out of the transmitter, where you will have the desired signal, which will be these desired subcarriers, and you will have the undesired red guys. Many of them will be there because there are many subcarriers, and based on how far the subcarriers are, you're just going to have a lot of these red guys at the bottom. That is noise. Okay, and that actually will determine signal to noise ratio in the TX. In the TX, the signal to noise ratio really is determined more by non-linearity and not by the noise of the block itself. Because when the signal is very strong, you're pumping out a lot of power. Your nonlinear components are also much more stronger than noise itself. And that determines the SNR, which eventually affects what we call as EVM. The TX EVM, you can look it up, EVM and all that, but this is basically like, it's like a constellation picture of various, pretty stars all around, and if your noise is very, very low, you will have a very clean picture of stars, very regularly arranged, but otherwise they will be blinking a little bit more this way, that way because of noise. But you can look it up there, and eventually that's how we actually say how good a transmitter is. When it's transmitting a signal, is how much is the noise component in it. Based on that, it determines the EVM of the TX. So these unwanted signals that has now been formed in band, okay, will determine your kind of an SNR. Remember, there are many of these signals here, many of these subcarriers, okay, they're distributed all around, and that's why they're going to create all this IM3. Now, one thing that I do want to tell you is, when you have thousands of subcarriers, not all of them will be in phase. By that what I mean is, let's say if the magnitude of each subcarrier, as an example, was, let's say, 1 volt. Okay, each of them is 1 volt. Every carrier is going to have a magnitude and phase. Every subcarrier is a sine wave. If you had 1,000 subcarriers and they all are in phase at the same time, that is, they all line up such that all the 1,000 sine waves have the same phase. They have the 0 degree phase, all of them at the same time, and then all of their phases match up. Then of course, at peak, when the sine wave peaks up, 1 plus 1 plus 1, you will add up and it will become 1,000 volts, right? If each subcarrier is 1 volt and there are 1,000 subcarriers each lined up in phase with the same phase, then you will add up at the peak and it will become 1,000 volts. That's not possible. Okay, and that does not happen. So what happens is, normally when you have many of these subcarriers, the way the information is coded, most of them are not in phase, and they will, that's what we call as peak to average ratio of a signal, of an OFDM signal. Again, you can go back and read some of it, but the bottom line is most of their phases are not aligned, and that's why the signal does not become too strong. Okay, so that's what happens. But and you're welcome to look at something called peak to average ratio of OFDM signals. So what I was trying to say is, when you make these IM3s are generated, they are also going to be generated in various random phases. So they are not going to all be in phase, that one IM3 generated here will add up to another IM3 generated here will add up to another. No, they are also going to be in phases. But at the end, this is noise, and whatever phase they comes with, they all cause a total noise in your channel, and it degrades your SNR. Okay, so that's what is the first case, which is the in-band. This does not cause ACPR. What is ACPR caused is this, and the definition of ACPR is, if this is your channel, okay, next to it you have another channel, which is what we call as adjacent channel. If you're transmitting, if you have won the spectrum and you are using that spectrum to transmit your things, like a mobile operator, you really should not be dumping a lot of noise in the next channel. because you have not paid for that channel. So you should not dump noise into it. Somebody else will use it, and you should not corrupt it. So there is a limit to how much noise you can dump into it, and that ratio of your desired signal to the noise or the garbage that you dump into the next channel, which is the adjacent channel, here is what we normally call as ACPR 1. Okay, there is a 1 and 2. 1 is for this adjacent channel. Along with the adjacent channel, there is alternate channel, which is like, so if this is your channel number n, this is n plus 1, then there is n plus 2. You don't want to dump a lot of noise in n plus 2 also. So there is a spec for that also. That is what we call ACPR 2. Okay, so that is what we call as, different specs will say, for example, cellular systems, the ACPR 1 is limited to 33 dBc. What it means is, if you're transmitting at some power, your noise should not be more than 33 dB. Okay, 33 dB, the noise should be less than 33 dB with respect to your transmit power. Okay, if you violate 33 dB and you say it's 32 dB below, no, then you're violating the spec. Okay, the specification. So that puts specs on ACPR 1 and ACPR 2, which is a measure of how much garbage you dump on somebody else. Now let's look at this scenario and how out of band IM3 actually causes most of this garbage. Remember, if we didn't have any non-linearity in the TX, there will always be noise, right? Our circuits will always cause noise and we cannot avoid it, and that is a different scenario to talk about, which is what we call RX band noise, TX noise going into the RX band and all that, but we are not going to cover all that here. But we know that our systems are non-linear. So if you have a scenario like this, two tones, they're going to create IM3 at some level, right? So that is how you have actually created a noise in the adjacent channel. So one mechanism to create noise in the adjacent channel is just pure simple thermal noise that's coming from all your power amplifiers, driver amplifiers, everything that is there. But that noise level typically is very low. If you were to meet 33 dB spec, where this garbage is 33 dB below your signal, that's really not a problem if you just consider noise. But when you are transmitting at an extremely high power levels, as this mobile phones and even Wi-Fi and all does, then the third order nonlinearity itself would cause a garbage, which would be significant noise in the adjacent channel. Okay, so that is the main dominant way how ACPR, or what we call spectral regrowth, this is also called spectral regrowth, because you had the signal here, you are causing the spectrum to grow more because of this IM3 components. Not only IM3 components, there is also IM5 components which will be there, and they also become significant sometimes. They may not be very much smaller compared to IM3, and so IM5 components, the fifth order distortion, will actually affect more and more what we call as ACPR2, or the alternate channel, how much garbage you're putting in the alternate channel. But this also has an effect in the adjacent channel. So here also you will have IM3 along with IM5 components that will come. That is all based on how these two signals, which two subcarriers you want to put. If I have 1000 subcarriers here, I could have different combinations, different pairs of these 1000 subcarriers, which will then put different points here of IM3s and IM5s. Okay, this is, again, as I said, this is just an illustration with two subcarriers to show how we are creating garbage in the adjacent channel and in the alternate channel. But as you have all these thousands of subcarriers, they're going to cause huge amounts of IM3 here, IM5 here, and a lot of IM5 here, and based on how much the phase and all of all those IM3 and IM5 components are, they're going to create an eventual power, based on the vector addition of different components with different phases. And at the end, what it looks like, it's just it's noise. So that is what is the fundamental behind ACPR 1 and ACPR 2. Next is, how about some simple formulas? Now that we know what is the reason it's generated, where does this noise come from? So it is really not noise, it's the non-linearity, the non-linear components which are acting as noise here, on top of just thermal noise. Thermal noise is always there, but that's way low. So the non-linearity is the dominant factor here. What are the simple formulas you can use as a designer? Okay, so as I mentioned here, these formulas that I'm going to talk about here, some of you might question and say, oh no, these are not accurate. And I would only say to say this is, I have used these formulas not to be accurate, but to do an initial hand calculation. These are only for estimations. Because ACPR, if you want to know a real ACPR, you have to put a real input, an OFDM signal like this with multiple subcarriers, and then you simulate it in tools like Cadence or Synopsys and other tools, and it takes a long time. And it will give you the output spectrum. It will show you the output is clean here but dirty here because the spectral regrowth and all the noise has come. Those simulations take long. In the beginning of the design, when you're doing it, you don't want to run long simulations. You want to do some initial hand calculations to derive, okay, since it's caused by IM3, what kind of IP3 numbers or what kind of, these kind of simple numbers I want my circuitry to have. You want to know those from simple hand calculations, and this estimation is geared towards it. Once you put together a circuit and you simulate in a simple way and you're happy with it, then you go into the long simulations where you put in a modulated carrier and you run some envelope simulations to see if this is the input to, let's say, PA, what does the output look like. It will show you the complete envelope with ACPR1, ACPR2 and all, so you can do that. So let's take this case. So what we do normally in RF world is, when you have an OFDM signal like this, we will estimate it, just model it by two tones. And it's a crude estimation, simple estimation, it works most of the time. So if you have a particular input power, output power, most of the time, in this case I'll just talk about output power because I think we will do the PA example, so we'll start with output power. So if you have an output power specified, we will model it as just two tones where each tone is output power minus 3 dBm. So for example, if the output power was 26 dBm, each tone here will be plus 23 dBm. Okay, we just take the 3 dB out so that the total power of these two tones is same as the total power of all these subcarriers. Okay, so this is a simple way of estimating it, going from a multi-tone signal to a two-tone signal. Now what happens is, if you have two tones like this, it's going to cause IM3 because the third order nonlinearity will cause IM5 also. Let's not worry about IM5 or ACLR, ACPR2 and all that. So we'll just talk about IM3 for now. And a simple formula that works most of the time is, if you want to know what is the ACPR, okay, then a simple formula is, what is this IMR3? That is, this is say your P output that you're pumping out minus 3, right? For example, it's plus 23 dBm as an example. If you know what your IMR3 is, to that you can simply add a factor of 5, and that works most of the time for LT systems or Wi-Fi systems, which are where the modulation schemes are higher. That is, signals with higher peak to average ratio, signals with a lot of subcarriers, which end up with and causing a lot of higher order modulations, trying to get higher data rates. There, in those kind of systems, also end up with higher peak to average ratios, and for those kind of systems you can use this simple formula. Why I'm trying to show this formula is, you might have a circuitry which you know that, oh, for this particular output power level, I know this IMR3 is this much. Then from there you can simply estimate what the ACPR would be, because at the end you're trying to design for an ACPR, and we will just do that just in a minute. So this simple formula works mostly for LTE or higher modulation type systems with high peak to average ratios. In case the modulation is not so high, or you're not trying to send a lot of data, or your peak to average ratios are lower, then this factor of 5 you could also estimate as about 8 to 9, which is 8 is the number roughly around for like WCDMS systems. So if this was a WCDMS system, it will also have many subcarriers, but there you can just take the IMR3 value and add about 8 to it, and it will give you ACPR value. Why it is so? Because remember, here there are two tones which is giving an IM3, right? So you've got an IMR3, but this two tone is only representing a simple a simple scenario with these multitones, right? When you actually have these multitones, you will have many IM3 components will be generated. They are not going to be in phase. So by doing this to this, we have actually put a constraint on us, saying that they are all in phase, and that's why this will actually generate a stronger IM3. But if there were many and many carriers, right, and you had many and many IM3 generated, all those IM3 components are going to be in different phases, so you will not add all of them up in the same phase, and that's why you get a little fudge factor. We call it the fudge factor, which comes from much more detailed modeling in MATLAB of OFDM signals, also from measurements in the labs, and you come up with some factor which can be used in HAL calculations. Now let's take an example. What does all this mean that we have derived it, but how do we apply it? Let's take the case of a PA, as we're talking about a power amplifier. Let's say the gallium arsenide power amplifier for LTE. Let's say it's trying to pump out 26 dBm output power, and maybe its gain is 26 dB, just as an example, where the input is 0 dBm roughly. I have it shown differential, but it's really not differential, it should be single-ended. So that's a mistake on my part, I'm sorry about that. So you have 0 dBm, 26 dBm, and we say we want an ACPR of 40 dB from this PA. Typically these PAs are designed, the gallium arsenide or any other CMOS PA is also designed to be much better ACPR than the spec. The spec, the 3GPP spec for cellular is 33 dBc is the ACPR spec. Okay, so we will design it with some margin, and typically 40 dB or better is a good number to have. Now we say that okay, ACPR is roughly, let's say it's an LT case, is plus 5. So what should be IMR3? If ACPR is 40 dB, IMR3 would be roughly 35 dB. So what this is saying is, at the output, if I were to model that thousands of subcarrier type OFDM signal that's going out by just 2 tones as shown here, each tone will be 3 dB below the power. So 23 dBm, 23 dBm, right? Total power of these two will be 26 dBm. And we want an IMR3 of, as we just calculated, is 35. So if I have an IMR3 of 35, it will roughly give me an ACPR of 40 dB. If I just do this, I don't need to know how low this the output IM3 value is. OIM3 is output IM3 because this is also P out. What I can directly calculate is what should be the output IP3 of the PA. The output IP3 of the PA should be the fundamental power, which is 23 plus IMR3 by 2, 35 dB by 2, which should be roughly around 40 dBm. So that's a pretty big number. If you have designed linear circuits and nonlinear circuits, getting such big numbers in the order of 40 to 45 dBm is very, very difficult from CMOS, and that's one of the reasons why most of these power amplifiers are still gallium arsenide. They're bipolar and they're very, very linear. They're inherently much more linear than CMOS guys. So the output IP3 could be a very big number, as it is this, and you will need that to get an ACPR of about 40 dB with a P out of about 26 dBm. Now if you have an output IP3, you can also calculate the input IP3, which will come as simply output IP3 minus 26 dB is the gain, so input is about plus 15 dBm. These are very big numbers. Just in CMOS you can't just get plus 15 dBm type of linearity from just the CMOS devices. It's very hard. That's why they do a lot of non-linearity cancellation techniques and all that. Gallium arsenide inherently is more linear, so it's a little more easier to do it in gallium arsenide. Not that it's a slam dunk case. You still have to do some non-linearity cancellation and improvements there to get these numbers. But why are these numbers important? Now if you have a circuitry in mind and you say, hey, I have this PA, I just want to know how linear it has to be. I don't know how linear it has to be. Well, now you know. It should have an IP3 spec of around plus 15 dBm, and it should have an OIP3 spec of roughly around 40 to 45 dBm. With you put some margin on it, and that will be better. That gets you the starting point to calculate what should be my spec, because you cannot really put a circuitry, some fancy circuitry here, and try to push in, your OFDM signals to see, okay, what kind of ACPR do I get at the output? No, you have to be able to know what should be some of the non-linearity specifications like OIP3, output IP3 or input IP3. You have to be able to have some idea of what those numbers are before you actually start designing it. Okay, so this exercise is geared towards how you can find the simple calculations to be done. Similarly, I think we already talked about this. Let's go back. So we did the PA, power amplifier part. Duplexers are passive, so they're going to have huge IP3 numbers anyway. One of the things you also have to keep in mind is if you put switch somewhere, typically after the duplexer there is a switch. Those switches also have to meet these kind of huge input IP3 numbers, because the switch, it doesn't have any gain in it, so its input IP3 has to be like around 45-50 dBm type numbers. So that's why those specialty switches, even though it's a switch, they're actually very expensive. Anyway, I'll not go there. So we did the PA part. Now I come back and say, okay, I'm going to design a driver amplifier here. Maybe it has a gain of 10 dB, where the output is 0 dBm and the input is then minus 10 dBm, right? Just as an example. I don't know what the circuitry is, but how can I derive how linear does it have to be? So how much ACPR should I put as its spec? We said that PA is about 40 dB, see, ACPR, the ACPR spec, so we had an IMR3 spec from there. So how about this? In DA, we will try to target it to be much more linear compared to the PA. It has to be. Otherwise, this nonlinearity will start getting on top of this and start, destroying the system. So we will say that DA, we want it to be 10 dBs, better. So the ACPR of the DA, just as a rule of thumb, let's say it's whatever the PA was, will have a 10 dB margin to it. So we want an ACPR of 50 dB. And typically in cellular, at least, we know that these DAs are designed to have 50 or 60 dB type ACPR numbers. So if it's 50 dB, then again we look at this thing as the output of the DA, where it's trying to pump out 0 dBm. So I'm modeling it as two tones. Each is -3 dBm. And what should be the MR3 number there? 45 dB. Because if ACPR is roughly 50, you take 5 out of it from our simple formula, it will be 45. So now if this is what you want at the output of the DA, now you are ready to calculate what should be my OIP3 number. What should be my output IP3 number of the DA. That if you calculate will come around plus 20 dBm, which is also pretty high. Okay, and input IP3, if you calculate accordingly with the gain being about 10 dB, will be about plus 10 dBm. This is also a pretty big number. It's not easy to, if this is done in CMOS, which is what pretty much all these circuitries are in CMOS, there is fair amount of work that goes on to make an amplifier which can have an input IP3 is around plus 10 dBm. Okay, and that's one of the points that I wanted to stress. But what I'm trying to stress on is there is a way you can design the system yourself, treating DA as a black box, and deriving what should be the linearity numbers, and from the linearity numbers then getting to the circuitry and figuring out how I'm going to design it. Okay, and once you have done all this, then you can put this TX chain. When you have done it for DA, where you have done it for mixer, BBF and all that, then you can actually simulate this whole chain with actual OFDM signal at the input, and that would actually show you what the ACPR of the whole chain is. Okay, but we're not trying to do it to start with when we're trying to design the things. One last page here, since we are talking about DA. The typical circuitry of a DA is, I've just shown two simple circuitries that we use in case you are wondering what the circuitry looks like. This is the case where the input is single-ended, the output is single-ended. Most of the time this is not the case. The input is mostly differential and the output is single-ended. We will have a case like this, but let me just go over this first, where it's a simple NMOS based inverting amplifier with a cascode device for isolation. And then you have an LC tuned load at the output to tune it to the frequency at which you are trying to transmit, like 900 megahertz or 1800 megahertz, 1900 megahertz, 2100 megahertz, 2400 megahertz, whatever it is that you're trying to transmit. So it takes an input, it's a simple amplifier, then you do some AC coupling to do the 50 ohm match, because most of these now come with an internal match. The DA, you have to match the DA output single-ended to the PA's input. PA's input is 50 ohms, DA's output has to be 50 ohms. So that matching is done just by, in a crude way of just putting a 50 ohm. It does cause a lot of wastage of power there, but that's the simplest way to do such a match rather than using external LC components. You can also achieve it with using external LC type matching networks to do it, but just to avoid external components, we just, in most of the cases, we do it this way. So this is a 50 ohm match, and this goes out. The differential circuitry is shown here, where you have a differential input stage coming. This helps in separation, good separation of the even order harmonics. All this time we have only been talking about the order, like third order, fifth order, mainly the third order. That is true for this case, where the even order harmonics will be more suppressed. But again, here you have the input, cascode, tuned load, using a transformer, and then going out to drive this output, which will drive the PA. Now, one of the key things I say is if the IP3s have to be this high, like plus 10 dBm at this input, okay, that what it means is, and when you get to do these designs, or if you've done these designs, you will see that means a lot of power. So these driver amplifier type circuits actually end up burning a lot of power, and not just a driver amplifier. Anything like a driver amplifier, anything like a power amplifier, they burn a lot of power to get, not because they need a lot of gain, but they need a lot of linearity. You have to bias the devices in strong inversion and do other things. By burning power, that becomes feasible and you get more linearity. So you're trading power versus linearity. So that is the DA. Then the stages before that, I have not gone through a lot of calculations or anything, but I just want to briefly cover this with you. You have the mixer before it. Before that, you have a baseband filter to filter out mainly the noise and all the aliasing effects, the clock aliases that comes from the DAC. But the main thing is, if you look for ACPR, what you're trying to do is now you have to make sure that at each of these stages we have good linearity. We have enough IMR3. So if we said that the PA is 40 dB type ACPR, the DA is 50 dB type ACPR, these things we design it typically with 60 dB or better type linearity numbers for IMR3. So the mixer, if you look at the linearity of it, you want its IMR3 to be very good. You can back calculate what the IP3 could be just based on how we did for the DA. We did the DA's calculations, and based on this you can do the calculations for the mixer, you can do the calculations for the BBF, you can do the calculations for the DAC also. But the point is that they have to be much more linear, so they do not affect the overall ACPR at the end. We want the overall ACPR at the end to be affected only by the power amplifier, the PA. Rest of the stages should be much better. There is another reason why the IMR3 we need higher IMR3 in LT systems, and this is because of a phenomenon called 4F mod. You can look at the literature to see what does it actually mean. There is a lot of detail, and it's a very complicated phenomenon, but what it does is it goes through not just a primary mixing, secondary mixing of various third order and fifth order and other harmonics, but at the end what it does is it actually puts a lot of constraint on the baseband filter. Okay, this filter stage here that you have, filter stage in the DAC and also the mixer, it puts a lot of third order IMR3 or IP3 type, third order distortion in general of the DAC and the baseband has to be really good to help with the 4F mod problem. And in the mixer, what happens is sometimes the mixer's third order, the 3 LO, when you have an LO coming in here, you have a clock coming in, right, which is what typically we call as LO. I have it in the other lectures. You can refer to the other lectures and see how this mixer, what are the things coming. But when you have a square wave clock coming in LO, you will also have 3 LO. That 3 LO component causes a lot of issues with 4F mod. This is what we are talking about. And to overcome that, sometimes we have to use HRM mixer. HRM is harmonic reject mixer, which helps the rejection of third and fifth order components of the LO signal and helps with this problem. But this is just as a side note, should not be a distraction to what we just went through, which was how is ACPR caused, what are the main fundamental, the nonlinearity causing the ACPR, how you can step by step treat your circuits as a black box and derive some of the key specs like the linearity specs, the output IP3 or the input IP3 of these things. So hopefully now you have a better picture of this. So this only covers ACPR. I'll try to do some other lectures on other aspects of the TX. So thank you all for watching.